To Sarah Wells. She's an associate professor at the School of Biomedical Engineering at Dalhousie University. She did her PhD in materials and biomedical engineering from the University of Toronto and her postdoc in bioengineering at the University of Pittsburgh. She's jointly appointed in the Department of Physics and Atmospheric Science and also in the School of Biomedical Engineering at Dalhousie University since 2000. And she's now an associate professor, as I said. She's also the assistant dean for the Medical Sciences BSc program. She teaches physics, biomedical engineering, and medical sciences, and she received the 2019 Dalhousie Academic Innovation Award. Her research uses a material science approach to study the structural and adaptation of cardiovascular tissues during pregnancy and development. She's an advocate for women in STEM she's an advocate for women in STEM, and she's spoken about this topic as well as her research topic in the media quite frequently. So we're really excited to have her here today to talk to us about the strength of a mother's heart. So Sarah, welcome to the NSIS, and we really look forward to your talk.
Thank you so much for inviting me. It's my pleasure to come and talk to anyone who wants to hear about my research work. So as said in the introduction, I'm going to be talking about my research area, which is material science approach at looking at how the cardiovascular system adapts to different physiological conditions, including pregnancy. So I'm one of the principal investigators in the tissue mechanics lab here at Dalhousie University. And our lab primarily is interested in the relationship between the structure and mechanical properties of tissues. And in particular, I'm interested in soft tissues and soft cardiovascular tissues, including the heart valves, pericardium, and aorta. And basically, so, I mean, my PhD, as mentioned, is in materials engineering, and that's really materials engineering, looking at the link between structure and properties or mechanical properties, mainly in my case. And so when I talk about soft tissue structure and mechanics, I'm mainly interested in soft tissues that are mechanically load-bearing in the body. And all of those soft tissues have two major components to them. They're basically all built from two major protein polymers, elastin and collagen. And you may have heard of both of these structural proteins. Elastin is a polymeric rubbery material, as its name would suggest, very extensible with very high elastic energy efficiency. So when it expands, it recoils with great efficiency. So elastin is like a rubbery, a biopolymer rubber. And collagen, on the other hand, is like the stiff, strong, biological tensile wires that you would see, sort of the similar tensile wires you would see in a suspension bridge. So collagen, also a protein polymer, is very stiff and very strong. It's comparable to, steel wires. And so we've got two very, very different protein polymers that together comprise soft tissues as composite materials. So most of your soft tissues, arteries, skin, heart valves, all have some combination of elastin and collagen. And the net mechanical properties or net behavior of that tissue is determined by this equation up here. The very, very basic simplified version of this is that the overall properties of the tissue is a summation of the sum of the volume fraction of each component times the mechanical properties of each component. So if you had something that was 50-50 collagen and elastin, the properties would be determined equally by those two components, with the caveat that properties are also determined by the arrangements, the three-dimensional arrangements and interconnections of those components. So this is like the 1 minute soft tissue materials science overview. Collagen, elastin put together in various proportions and arrangements to produce mechanical properties tailored to that particular tissue type. So collagen and elastin together both give extensibility and strength. And so how those properties are determined in the tissue as a whole will be determined again by how much of these components are in the tissue and how they're put together. So if we look at the stress strain curve for collagen, again, this is the stress applied to a tissue versus the strain or the resulting deformation. So this is much like the force versus extension curve that you would have for a spring. The slope of this curve is the stiffness, or the Young's modulus, the elastic modulus. So when you have a stress strain curve, you apply a stress, you get very little deformation of collagen because collagen is very stiff. It resists deformation. Elastin, on the other hand, like I mentioned, is this rubbery polymer. You can apply a very low stress to it and get a resulting very large strain to it. So it consequently has a very low stiffness. You can see the slope of this curve is much lower than collagen. So this isn't surprising. You've got stiff collagen, extensible elastin. And these two components are put together in tissues in parallel. So here's my model of soft tissue, elastin and collagen placed in parallel. And this is a very simplified model, but this is what it would look like. My elastin is my rubber band and the collagen is the metal chain. Now, the way these tissues are actually arranged in most soft tissues is that the collagen is not straightened out under normal loading conditions. So this would be in your heart valves, your aorta. Under your normal blood pressure conditions, the collagen fibers aren't completely straightened in tension. They're actually wavy or crimped. And this is what the scanning electron micrograph would look like of those collagen fibers under normal blood pressure conditions. So here's my parallel elastin collagen model. This is my model of soft tissues under moderate physiological loading conditions. This might be, say, your aorta. So under normal blood pressures, your aorta is this expandable rubbery tube. It expands and recoils with each heartbeat. So under normal blood pressure conditions, you have a rubbery tube with nice elasticity and elastic recoil. If your blood pressure goes up too much, the collagen becomes engaged or straightened. And now you have a material that's very stiff and strong and resists overexpansion or fracture. So this parallel elastin collagen model, you can think of it like a garden hose. You see those garden hoses, a rubbery garden hose that has that steel meshwork through it to prevent the hose from overexpanding. And this is the basic model of all the tissues I'm looking at. Heart valves and aorta that function elastically under normal operating conditions. If they're overloaded mechanically, the collagen becomes engaged and prevents overexpansion and rupture. And so that gives it's a great example of composite structure and function. At normal pressures, you have something rubbery. At high pressures, you have something stiff and strong. And so this is the basic arrangement that I'm interested in load-bearing soft tissues like heart valves and aorta that have to undergo not just high mechanical loads, but repeated cyclic loading conditions. Every time the heart beats, heart valves have to open and close, and the aorta has to expand and recoil. And that puts an even greater challenge on these biomaterials because they not only have to have the proper mechanics to function under normal physiological loads or very high supraphysiological loads, they have to be able to do this millions of cycles per year and actually nonstop, as long as you're alive and your heart is beating. These tissues have to undergo that cyclic loading without failure. And it's remarkable to me that collagen, elastin, these soft tissues can even do that. Currently, we have no engineering material that can undergo that kind of cyclic loading, even for a period of, say, 15 years or something. If we want to make a heart valve replacement, We're lucky if that thing is going to function for more than 10 years, because cyclic loading is much more damaging to materials than a simple static load. So that's why to me, these tissues that are undergoing cyclic loading are even more interesting. And so I've talked about heart valves and aorta in particular, and this is just a particularly little bit creepy animation of the heart beating. And if I just bring that up on a new slide here, this is what I mean. In case people aren't familiar with how heart valves work, heart valves are soft tissue flaps that keep blood flow unidirectional through the heart. And so the ones I'm mainly interested in are the ones that link blood flow from the heart to the body. So here's our animation of the heart, and here's the left ventricle. And the left ventricle is pumping blood out the aorta that has to go to the whole body. So it's a left ventricle has got a thicker wall, more muscle, because that's a very heavy workload to pump blood out to the whole body. Every time the left ventricle pumps, the outflow valve is the aortic valve, and it opens, allowing the left ventricle to empty into the aorta. And if I'm able to get this to work. Okay, underneath that, so that's the aortic valve opening and closing. And also every time the left ventricle pumps, the mitral valve, this is the one-way valve that allowed blood to enter the left ventricle from the left atrium. When the left ventricle pumps, you don't want blood going out back into the left atrium. You want all the blood going out the aorta. So the mitral valve serves as a one-way valve that closes during ventricular contraction to prevent backflow of blood back into the atrium. So with every heartbeat, the mitral valve closes, preventing backflow. Aortic valve opens, allowing outflow. So we've got open, close, open, close, open, close with every heartbeat. Here's a video of the aortic valve taken from above, and the aortic valve leaflet is the aortic valve is made of 3 soft tissue leaflets that open and close together, allowing that one-way flow. The mitral valve is a little bit more complicated. It has 2 major leaflets that open and close, and backflow is prevented even further by these small tendons that lock the edge of the free leaflet down into the ventricular wall. And those are called chordae tendineae, like little mini heart tendons. These are the so-called heart strings that prevent backflow every time the ventricles pump. Similarly, the aorta, every time the heart beats, the aorta has to expand and recoil. And that's a challenging mechanical environment as well. And the aorta needs to have an extensibility and elastic recoil in order to drive that blood flow out the aorta. And this is called the Windkessel function of the aorta. I've got a video here, but it doesn't show very clearly. So I think I'm just going to describe this in the air. I want to just emphasize the importance of the mechanical properties of the aorta in delivering blood flow. So you have the heart pumping blood into this aorta, the tube coming out of the heart, and it's going to distribute blood to the whole body. If the aorta was made of a metal tube, you would have forward blood flow every time the left ventricle contracted. But in between heartbeats, you would have no forward flow in the aorta. So you would just only have intermittent flow. It would be like having a fire hose with a pump, and you would only have forward flow squirting out of the fire hose every time the pump squirted. Not a very efficient way of delivering flow. The aorta, as this rubbery elastic tube hooked onto the heart in parallel, actually acts as a second pump in series with the heart. So every time the left ventricle contracts, the rubbery aorta expands to allow that volume to come out of the heart. Some of that volume proceeds down the aorta, but some of it gets stored in that expanded area that the aorta fills up. in that initial